Good afternoon, and welcome to Hand-Wavy Chemistry, where we do not delight in the details, but rather bask in the big picture. Today, we're discussing formal charge and oxidation number. This video is being made in response to a user's comment where they asked for a video on electronegativity, polarity, formal charge, and oxidation number. The first video on electronegativity and polarity can be found by clicking the link up here or looking down in the video description. Now, on to formal charge and oxidation numbers. Molecules are made up of atoms that are sharing electrons. The way that they share electrons can be in a covalent manner, where each atom shares electrons evenly between them, or in an ionic manner, where an electron is formerly taken from one atom and given to the other. Or it could be somewhere in between, where a bond is somewhat covalent or somewhat ionic. Formal charge describes what the charge on each atom would be if the bonds were completely covalent. Let me show what I mean by talking about ozone. Ozone has 3 oxygen atoms. We can draw its structure with an oxygen double bonded to an oxygen with a single bond to the next oxygen. And these oxygens have a certain number of lone pairs. If we were to evenly now divide up the electrons in that bond, the double bond has 4 electrons. So we'll give 2 to this oxygen and 2 to this oxygen. Now, this one over here, it had 2 lone pairs already. So we have 1, 2, 3, 4, 5, 6 electrons, which is the normal valence state for oxygen. So we would say that it has a formal charge of 0. Now for our next oxygen, we've got 1, 2 from the double bond. It had a lone pair, so 3, 4, and 1 from the single bond. So it has 5 electrons. It is missing an electron compared to its normal valence state of 6 electrons. So in this case, we would say it has a formal charge of +1. It is missing an electron. Electrons are negatively charged, so +1 is its formal charge. The final oxygen, it has 1 electron coming from that single bond, and it has 1, 2, 3, 4, 5, 6 electrons coming from lone pairs. That's a total of 7 electrons, meaning that it has 1 more electron than it would normally have. So it will get a -1 charge. If we add all of these numbers up, 0 plus 1 minus 1, we get an answer of 0, which is good because ozone does not have an overall charge. The formal charges should sum to the charge of the molecule, in this case, 0. There are slightly differing conventions in how to represent formal charge, depending on if you are an organic or inorganic chemist. Organic chemists like to show the formal charge as close to the atom as possible, often drawing a circle around it. So we could represent the ozone molecule with its formal charges like so. Inorganic chemists and chemists that work with organometallics work a lot with transition metals. And there is some fuzziness in how you might want to account for the number of valence electrons that a transition metal has. So rather than assigning formal charges directly to the atoms within the molecule, they might use a corner bracket or square brackets and show the charge of the molecule outside of that, or simply omit it altogether. Because formal charge assumes that all electrons in a bond are equally shared, it neglects the ionic character of many bonds and compounds. So if we want to think instead in more of an ionic way, where electrons are taken and given, we have oxidation number. Oxidation numbers are the charges that atoms would have if the electrons in the bond were given to the more electronegative element. In cases where we have elements, so all of the atoms within a molecule are exactly the same, it doesn't make sense to say that one is more electronegative than the other. So we say that each of these atoms has an oxidation number of 0. So if we think back to ozone, before we said formal charge was 0 plus 1 negative 1, for oxidation number, they're all going to be 0. However, for other molecules that maybe had a formal charge of 0 for every atom in it, such as sulfur hexafluoride, we're going to get an oxidation number that is non-zero. If we look at sulfur hexafluoride, calculating formal charges, each of the fluorines has 6 lone pairs and 1 electron coming from the bond, taking it to 7. 7 is its normal valence state, therefore formal charge is 0. Sulfur has 6 bonds, so it has 6 electrons, which is its normal valence state, therefore formal charge 0. But for oxidation numbers, fluorine is the more electronegative number. So fluorine gets an oxidation number of -1 for each fluorine around that sulfur. Because the sum of the oxidation numbers must equal the overall charge of the molecule, the sulfur must have an oxidation number of +6. Because we have 6 negative 1s from the fluorines, we must have a +6 on the sulfur. When it comes to determining oxidation numbers, most chemists don't actually go and look at the periodic table. Instead, they remember about half a dozen rules. For example, fluorine is always -1. Pure elements are always 0. Hydrogen is usually +1, except when it is a metal hydride, in which case it will be -1. Alkali metals, such as lithium and sodium, they're always +1. And alkali earth metals, like calcium and magnesium, they're always +2. Oxygen is usually -2, unless it's a peroxide, in which case it's -1, or it's bound to fluorine, in which case it's +1. Other halides like chlorine, bromine, iodine are normally -1, but not always. And finally, the sum of all of the individual oxidation numbers must equal the charge on the atom or molecule. I want to finish off by showing some interesting flexibility that can be seen with oxidation numbers. By looking at chlorine. Chlorine is usually -1, unless it is bound to oxygen or fluorine. So I want to talk about 4 different polyatomic ions that all involve oxygen and chlorine. The first one is hypochlorite, ClO-. The oxygen will have an oxidation state of -2. The overall charge is -1, so the chlorine must have an oxidation state of +1. +1 minus 2 equals -1. Chlorite is ClO2-. Once again, the oxygen is going to have an oxidation number of -2. The overall charge is -1. So with 2 oxygens, that's -4. So the chlorine must have an oxidation number of +3. 3 minus 4 is -1. Chlorates are ClO3-. Now with 3 oxygens, The oxidation state on the chlorine is at positive 5. And then there is perchlorate, ClO4-. The oxidation number on the chlorine is now up to +7. Remember, normally chlorine is a -1, representing that it would normally take an electron. By saying it's +7, we're describing as all of those oxygens coming along and taking all of the chlorine's electrons away from it. It should come as no surprise, therefore, that perchlorate compounds are often explosive. When we were discussing formal charge, I made the comment that there can be some fuzziness about how you might want to count the valence electrons for a transition metal. Well, for oxidation numbers, we find that there are a range of different stable oxidation states for transition metals. But that is a story for another time. I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if you have a topic you'd like to see covered in a future video, please put it in the comment section down below. Thank you, and I hope you have a wonderful rest of your day.